Our learning goal for this video is to build on the previous video, and we're applying now the linear relationship between natural log of y and x. So we've got an example here to illustrate this, and this is apparently real world record times for women's 1500 running events over different eras, and we've got to develop a model for this data and use it to predict the world record time for this event in the year 2020. So this question is written prior to the year 2020. So hence the word predict. So that's just a bit of information if you happen to be watching this subsequently beyond the year 2020. So I'm also going to compare this with what's called an exponential regression using a TI-inspired calculator and talk a bit more about what will be coming up in that regard. So you can see in the first row of the table we've got various dates from the 20th century there, and we've got some times, as you can see there, minutes, seconds and tenths of seconds there. Now that's not very useful in that form. Neither of those variables that and the data really go together too well. So what we're going to do then is to convert time into a decimal year format, and we need a starting date, a starting year. So there's been a decision to make it at the beginning of 1960. There's no firm reason for that, but it does work fairly well. It's not immediately before 1972, and it's not back in the year 0 where BC became AD. That 1960 is one that will work fairly well. It's not the only way to do this modelling, of course. So using a simple little formula, days from the start of the year plus the year, current year minus 1960, and times that by 365 and divide it all by 365, we'll get the decimal data for years from the start of 1960, and you can see they're being converted down there. So time also needs to be converted into a better unit, and seconds works well here. So all of that there is turned into 245.1 seconds, and so on for the other data. Now in all of these we assume that the relationship between t, the world record times, and y, the other data, the number of years from 1960, is exponential. If it's not, well, there's two things you can do to check. If it's not, when we do the graph, our data will not match a line of best fit very well. It won't have very good correlation. Secondly, if you just plot the raw data, you can just have an inspection of the shape and see if it is a reasonable match to exponential data. Now, being modelling and using real world data, we're not going to expect it to be completely valid or particularly effective to use a model. It might be acceptable, but it will have some strengths and it will have some weaknesses. So very rarely to never is a mathematical model 100% valid. The point is whether the model is useful. Now you'll recall from the previous video that we looked at this in, relationship here. We investigated this relationship, and basically we found a match which was a linear relationship, which I've put in a condensed form just down there. We have different variables to y and x, so we need to adapt this now. So we have t equals a e to the k y, being a capital Y, and basically we need to rearrange as we've seen in the previous video. So cutting out all of the interim working, because you can go back to the previous video to see that. We get the following. log of t equals log of a plus ky, which fits y equals mx plus c form. So we can look at a linear model there. So that's beginning to apply that relationship there. So what we need is to add to our table, we need another row, because we're plotting the dependent variable as log t, and so the table there has to have that first row that we see up here, y, and it has to have this row. We don't actually need in this particular activity to plot this row here. Alright, we're going to find the log of time. When we do that, we see that it's pretty reasonable, but it's real data, so it doesn't exactly match this line. Now this line is not necessarily the best method to use. It's a line of best fit. It's got the advantage of being fairly easy to understand, easy to do, especially being a linear one, and it could be done by eye, which means basically you get once you got the points plotted, you get your ruler, and then you try and make the ruler fit the data as good as possible. On average, the line you draw should be as close as possible to the average of all of the points, so you should have about as much above as there is below. So you can do that by translating your ruler up and down the page and rotating it as well to change the gradient. There are other ways of drawing a line of best fit too. There's a method where you use 2 points, which you get by finding the mean of the upper set and the lower set of the data. That might not be very appropriate for this data. And there's another one where you find where you use just one single point, and again that might not be any more appropriate than just doing it by eye. So there are ways of doing it. They've all got their pros and cons. So because the data has a little bit of variation from the line of best fit, we need, once we've got a good line of best fit, we need to actually select a couple of points. Now choose points that are like very obviously or comfortably on the line, and you can see there in orange we've got 30 and 5.44. so there's 30, and we can see that does pretty much, yeah, seem to nail 5.44, and we've got 18. Alright, and that seems to go through 5.47. Okay, so pause the video if you need a closer look at that there. You'll note that those points in orange too aren't from the table. They don't have to be from the table, as long as they're clearly on the line and you can identify them with some certainty. They are reasonable points to choose that sit on the line. Next we use some U9 maths. So the gradient, we know our formula for gradient is y2 minus y1 over x2 minus x1, where we've got a point number 2 and a point number 1. It doesn't matter which one you choose as long as you're consistent, and so I'm going to choose or determine that that's 1 and that's 2. Alright, so we've got y of 2, which is 5.44 minus 5.47, and then we've got x2 30 and x1 18, and then we calculate that. So we've got a slight negative gradient of 0.0025, and in this video I'm not going to worry about describing the units for that. Now for the next step you've got a choice. I'm going to use just the gradient intercept form, our old friend y equals mx plus c, but you could also use the point gradient form instead, which you might recall is that's also usable. It's a personal preference, so I'm just going to show the outcome using the point gradient form. Okay. Regardless of which of those two that you use, you're basically putting in, you've got to find the gradient first, and then you're actually putting the gradient in plus a point, and it doesn't matter which point. Choose one of these two is obviously the best way to go. You can see that it's point number 2's been chosen, and the thing that we don't have then is the intercept, so that's what we're chasing next. So that's 5.515 once you do some rearranging in the line above. Now it's time to align our symbols with what we were working on here. We had M, but remember it's not quite the same. We've got here, that's our C, and this one here, alright, we've got K, so we're choosing M, K over M, that is, so we need to do a swap, and we need to do a swap here with C and log A. So let's do that now. K equals M, which equals 0.025. Now C equals log A, which equals 5.515. Convert that to exponential form, because remember, natural log is log to base E of A. So converting that to exponential form, we've got that, which is a real number. Get about 248.4. In questions like, so that's an exact value, but with some models it is actually more useful to have a decimal approximation, and that's the case in this model here. But of course it's not exact, it's a decimal approximation, which limits the model slightly. So rewriting all the information in a meaningful way, we've got T equals AE to the KY, which in this model we have 248. I guess if we put approximately equals 248.4 E to the negative 0.0025 Y is our model. Now a smart person will check to see if that's working well. It's this is one way of checking the reasonableness and validity. Okay, so validity, reasonableness. Okay, and what we mean is, looking at the table here, you can see how it's going. Not too bad, especially in the latter data. It's fairly close. If you wanted to, you could really go to town and look at percentage difference and comment on that. Okay, so you could look at how the predicted time varies as a percentage of the real time if you really wanted to get stuck into the reasonableness or validity of the model and how precise it is, if you wanted to get into a discussion on that. To make sure we've answered the question that was asked, we're looking at the year 2020, so that's 60 years after 1960, and so we turn to our model and work that out, that being the expected time for the 1500 meter race. So let's get in now and do that. We've got T equals 248.4 E to the negative 0.0025 times 60, and sub that in and crunch our answer. We get approximately 213.8 seconds. Now we can convert that into minutes and seconds and tenths of seconds, because that's what we had originally. So 3 minutes 33.8 seconds would be the expected or predicted time. Now, as a note, it is possible to do this or a similar process on graphics calculator like the TI here, but what I'd like you to know is that I put the data in into the spreadsheet and labeled log T and Y, and then graphed it. And you can do what's called a regression. This is a separate skill. It's not to replace what I just showed you, but this is another skill which I'll go into more detail about in a future video. But I just want you to compare what we got, and you go into it by that. And mine's got hide exponential because I've already used it, but you would click on show exponential, which would normally be there, and you get a linear line of best fit there. Sorry, a few technical issues there. Apologies, I said the wrong thing. We don't do linear. We do linear regression, not an exponential regression, because we're plotting the logs here. Okay, so remember, you can add your variables by clicking there and there on a T inspire. And sorry, it is a linear regression because we're plotting the log, not the raw data. If you're plotting the raw data, you do an exponential regression like I just showed you. So just to clarify, you go into regression and see it says linear up the top, and that's the one you want. Okay, now another thing too, as a nice option, if you go to settings, just if you want the R squared value, just go diagnostics, click, and I think you can make a default by pressing that there, and that will give you an R squared value, and the closer that is to 1, the better that is. 0.718 is fair but not awesome, so it's got some issues as we outlined before. And if we compare that to our function from before, if we go back and compare that here, and we saw that the points don't quite fit, just like in our graph, and also the finished graph is 240. Sorry, it was the linear graph was this one here, the equation I should say, and if we compare that to what you see there, you got 0.002517 for the gradient, and that's close to what we got, and 5.52 approximately, and we got 5.52, so pretty good. So it works well, and we're comparing it against